So we split this chapter into two main lectures, one on the first two sections, 13.1 and 13.2, and one on the second two sections, 13.3 and 13.4. And what we really want to focus on today is a lot of the relationships that exist amongst the variables. And today in the simulation, you saw a lot that was going on with wavelength and frequency and amplitude, and you were able to come up with some general conclusions. We're going to take that idea and extend it even further here during the review and talk about, well, what equations have we also gone over that are useful to discuss what happens as something changes. So let's start with 13.1 and 13.2. In that section, the first thing we talked about was period and frequency. Okay, we talked about oscillations and harmonic motion and a spring mass versus a pendulum, and there was a lot. We've discussed a lot of theory. We spent almost 4 lectures just on theory and then about 3 or 4 on lab. So the main formulas that we started with, we had 3 of them. We started with this one, which told us that omega equals 1 over tau. We also had tau equals and tau equals. One was 2 pi root m over k. And one was, 2 pi root L over G. Okay, so these are the formulas from 13.1 and 13.2 that were important, that really do explain almost everything in this section. These 3 formulas give me all the information I need for the whole section. And let me go into a little bit of detail here. So, the first thing I recognize, by the way, Eric, happy birthday. It's your birthday today, right? Yeah. Happy birthday. I just thought about it, I just clicked when I was looking at you. What I recognize here is that the frequency and the period are inversely related to one another. And that makes sense because we've talked about what they physically mean. And that's the biggest issue I think I've noticed in the last few years. People forget what they actually mean. So let's go over this. Let's start with period. That's the easier one. What does period mean? Physically, what does it mean?
The time it takes.
The time it takes. Good. The time it takes. Now, specifically, you were about to continue. I know that, Gus, but I wanted to just get another question out there. Specifically, the time it takes to do what? And this is where there's a little bit of confusion at times. To complete one cycle, okay, good. Specifically for a pendulum or a mass spring, give me more detail.
The spring would be oscillation.
It'd be called an oscillation, good. Give me detail about the physical nature of what one cycle is.
For it to return back to its original point?
Yeah. So for a pendulum, when you start up here, it has to go through equilibrium, up to the other side, back through equilibrium, back to the original point. That's one cycle. That's one time period. Okay, that was useful, especially for your problem set. You should have known that, because one of your problem set questions was about the time it takes to fall from max height to equilibrium. Well, that's a quarter of a cycle. Another quarter cycle, another quarter cycle, another quarter cycle. That's one full cycle, 4 quarters. Yes?
Why is it a quarter?
Because what is this from here to here? How much?
3 quarters?
No. Okay, so this is 1. So this is just half. And then half of half is 1/4. So think about it as parts, right? If this is one cycle like that, I've got quarter, 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 quarter. 4 quarters gives me 1 whole. Okay, so each of these little segments is a quarter of a cycle. For the pendulum. For the mass spring, it's very similar. If you have a mass spring and you release it from rest and the weight pulls down, as it pulls down, it goes through, back up, and back to equilibrium. So try it again. You literally let go of the mass, it pulls down, goes back up, compresses, comes back to equilibrium. That's literally one cycle. What is frequency? What is frequency now?
How much it oscillates in 1 second?
Good. How many times it oscillates in 1 second? How many cycles per second? Again, it's the other opposites of each other, really, or inverses or reciprocals, the right word here. The frequency is the amount of cycles per second. The time period is the time it takes for one cycle. So it's time per cycle versus cycle per time. They're literally reciprocals of one another. In the next 2 equations, what I want to start pointing out is a lot to do with relationships. And let's discuss what's happening here. This is the pendulum over here on the right-hand side. And then this is the mass spring system. on the left-hand side. Now, for the mass spring system, tau, again, is the time period it takes for oscillation to occur, one oscillation. Well, look at the formula. It looks like it's going to take more time if I have more mass. Why is it going to take more time if I have more mass? How are they related to one another? What's the word for that again?
Directly.
Yeah, directly related. So there's more time taken because the mass would go up. These are directly related. Well, you didn't really go over that in the lab, right? You didn't discover that. But in the lab, you did discover that the length of the pendulum is what alters the time it takes. That was the only thing that changed the time. Believe it or not, the amplitude didn't change the time. The mass hanging didn't change the time. It was the length of the pendulum that altered the time it takes. And that's right out of your formula. Look at the formula for the time it takes for a pendulum to move in harmonic motion. The time is directly dependent upon the length. The time for a mass spring is dependent upon the mass. Make sense of it. If I have a heavy object and I release it, what's it going to do? It's going to pull the spring further down. A lighter object with very little mass, I release it. What's it going to do? It's going to pull the spring maybe this far and then shoot back up, right? That's real quick. It would be real quick oscillations. A heavy mass would cause it to droop and then come back all the way up. So the heavier the mass, the more the time. The longer the pendulum, the more the time. How about the inverse parts now? It looks to me as if the time it takes for a mass to oscillate up and down on a spring is inversely related to the stiffness of the spring. Think about from your lab how that makes sense. You determined the K value in the lab for 2 springs, right? One of those springs, you added mass to it, didn't stretch very much. It stretched a little bit more. The other one stretched a lot. The one that stretched a lot was the weaker spring. It had the lower K value. That's what you determined with this law. So the lower K value is what we got. Well, think about it. If you have a lower K value, lower this number, what is it going to do to this number over here? Yeah, it's got to increase this one because these are inversely related to each other. So a lower K value means a really weak spring. A really weak spring set into motion would oscillate with big oscillations, with really large oscillations. Something with a really strong K value, it would not cause the spring to stretch very much. So the oscillations would be really short. It would be low value here. And then how about gravity? Why does this last part make sense? Why is tau inversely related to gravity? Somebody explain this notion over here. Why is it inversely related to gravity? What do you think? Marilyn, good.
Like physically or just numerically?
Physically, numerically, either answer. Numerically, I mean, it's kind of obvious.
Yeah.
Do you know why physically?
Maybe because gravity is pulling it down, so it takes more time. Because when it's longer, it's more time.
Forget the length, though. Just use gravity only.
Okay.
You're right. You had the right starting point. Gravity pulls it down, so answer the question or answer the statement with a relationship.
If
So
I'm seeing like a pendulum, I would think gravity makes the string longer.
no, the string is always in full tension. The length of the string is not changeable, let's assume for now. So we're trying to figure out these two here, right? Somebody help her out. Give her a little hand, yeah.
If there's less gravity, like if there's a less gravitational pull, then it takes longer to...
Why, though? Yes, you're right. If there's less gravity, if this goes down, time goes up. Absolutely. But why is that? Physically, why? Travis?
Gravity is the force pulling down. So if there's more of that force pulling down, the pendulum is going to swing faster. And if there's less of that force, it's going to swing slower.
Yeah. So what he's relating it to is really the frequency, which is inversely related to the period. More gravity means it swings faster. If it swings faster, it's going to have a lower period, a shorter time. Yeah, Marilyn?
I think I just got it's like acceleration.
Yeah, that's exactly what it is. Very good. It's like acceleration. Very good. G is acceleration due to gravity, 9.81. So if I go to Jupiter and I want to measure gravity on Jupiter, I can take a pendulum with a given length, I can take a stopwatch and measure the time it takes, right? If I know the time it takes and I know the actual length of the pendulum, I know tau and I know L, I can solve for gravity on Jupiter. Well, I know that gravity on Jupiter is stronger than the Earth. It's a lot stronger. It's like triple the strength of the Earth. So the time period of a pendulum on Jupiter would be about a third of the time period. Well, not a third, because it's under the radical. It's the square root of 1/3. But it'll be less than the time period on the Earth. On Jupiter, the pendulum, instead of going like really slow, like on Earth, back and forth, it would probably go like this. It'd be a lot faster. On the moon has much less gravity. So the object's going to do this. It's going to literally move in like slow motion. And you've seen like, I don't know if you've seen it before yourself, but like animations or like simulations of like an astronaut on the moon, when they jump, they don't return to the surface as quick because gravity is less. It's the same thing as what would cause the pendulum to move a little bit slower. Okay? So a lower G, a higher time period. It takes longer to travel. Yeah?
Would you ask about like if something like doubles by like this much, like this number, but if mass was double, or if you would times it by 4, it would just be 2 because it's under mass.
Correct. Yeah. So her question has to do with relationships here, and that's a good question. If the mass goes up by a factor of 9, you replace this with a 9m, and then the radical 9 comes out front as a 3. So the period would go up by a factor of 3. If the mass goes up by a factor of 16, the period would go up by a factor of 4. Okay, it's the same thing with the denominator. If the spring constant goes up by a factor of 4, yeah, you're going to bring a 2 out because it's a 4 under the radical, which is a 2, but it's in the denominator. So if this goes up by a factor of 4, the time period decreases by a factor of 2. Again, how are these related? How are these related to each other? What's the word for that again? Inversely. So if I increase the k value, this has to go down, right? That's why I use the word decrease there. But if I put a 4 inside of here, and I say, oh, you know what, I'm going to quadruple the k value. Well, that's the equivalent of saying, you know what, I'm just going to write tau like this. Literally, that's what you're doing. You're taking the 1 over root 4 out in front instead of leaving it inside, and everything else is the same. Well, what's root 4 again? Root 4 is just 2. So in the end, your time period will be half of what it was. Okay? So if you were to quadruple the spring constant, you take the time period and you cut it in half. Because these are indirectly related. If this goes up, this goes down. By what factor? By a factor of 2, it goes down. Or you could say it changes by a factor of 1/2. Either way is acceptable as far as numbers are concerned. Hey, what you need to recognize and be able to do, though, is not necessarily just plug in a ton of numbers. You can do that, but it's going to take you a lot of time. So try to pick up on these relationships when it's underneath the square root. It makes life a little bit easier on the test. It saves you time to complete the test. Okay, because if you try to pick numbers and you try all these numbers, it's going to take you a while to calculate all these facts. We talked about a diagram at one point in time. And this diagram, I forget what section of your book or your chapter it was in. This diagram is pretty much what we have right here on the board. If I release a pendulum or if I release that mass spring, it's going to start to oscillate down and then it's going to come back up. So this guy, in an instant, will be a little bit stretched. And then let's say that's at equilibrium now. And then after the next instance, it's stretched even further. Here's equilibrium. Now it's stretched all the way down to here now instead. Whereas the pendulum will look like this. At this instant, it'll be at equilibrium. And then over here, it'll be on the other end. So this motion, where you release a mass or release a pendulum, they both are going to travel through the equilibrium position, and then they'll stretch the spring or they'll extend the pendulum upward. And then what will happen afterward? The pendulum will come back. Well, the spring will also come back up. Yeah. Yeah, I know. Leave that one. I'll figure that out. I couldn't figure out what that was. She did it on her own. She was out of the lab.
All the other ones are good enough.
Thank you. When you're done with what I told you, you can go. That's what I want to do today. So if we look at this, we could say to ourselves the following. First, at this instant in time, right here and here, these objects both have a lot of energy. They both have potential energy. Then the object starts to fall. It starts to fall. At the bottom, it's got all kinetic energy. A lot of kinetic energy here at the middle. Then, eventually, it causes this spring to stretch, giving this more potential energy. This one passes through equilibrium and comes back up to here, and that's the third instance over here where it has now potential energy. In class, we talked about this being like a spring force. So the way I like you to think about it, if you think about it this way, look at the third case. It's the easiest one to analyze. So look down here at the bottom. If we look at this, we can see that the spring itself is stretched way beyond equilibrium. So it's going to want to pull back up. So the force, thank you, due to the spring is acting upward. So there's acceleration upward. Well, what's the velocity when it reaches the bottom here, though? This spring gets released, right? Or this mass gets released and starts to fall. Eventually it gets to the bottom. Before it starts to come back up, what's the velocity there at the very bottom?
0.
Yeah, it's 0. So we know that the velocity here is 0. Well, it's the exact same case over here. This has gravity acting on it. So there is acceleration. These are both at maxes, and velocity is 0. Now, it's kind of the opposite when it's in equilibrium, though. When it's in equilibrium, the spring is neither stretched nor compressed. So at this state, there's no force in the spring at all acting. So there's no acceleration here. But we'll notice that the velocity is at a max at this point. The same thing happens here. When it's at the bottom, the velocity is as fast as it can go. Right? It picked up speed. It got faster, faster, faster. It's as fast as it can go when it gets here. Then it slows down. Speeds up, slows down, speeds up, slows down, speeds up, slows down, etc., etc. So at the middle point there, you have max velocity, but there's no gravity and no acceleration. Okay? Now, obviously, there is real weight to it, but we're saying if we consider that to be like ground level, we're not looking at that as far as energy is concerned. These are analogous to one another. So what's the difference in these scenarios? One has a spring that's restoring it back to its normal shape and size and location, while the other has gravity pulling it back to equilibrium over and over and over again. I think it's anything else for this. Let's go on to the next thing. We talked about also after this amplitude and frequency and period and wavelength. We did part of this in this section and part in the next section. So what I want you to remember is physically what these things are. So what is amplitude? On the graph I know you just did for your lab, obviously you knew that amplitude, right, was the height of this graph. That was the amplitude right there. But what is it physically with a system? What is the amplitude? Like for a mass spring or for a pendulum system or any system that's vibrating, a guitar string that's vibrating. What is the amplitude physically? What's the description of an amplitude? What? The key? What do you mean? It's the key to everything, the amplitude. So for example, this. Here's equilibrium. Here's the actual object. It's released from where it is. It passes through equilibrium. So what's the amplitude?
Why does it get from equilibrium?
Yeah, it's as far from equilibrium as possible. It's the max displacement from equilibrium. So in this case, it'd be measured by theta. Now, if I take this spring and I stretch it so that the spring now looks like this, so let's call the equilibrium white, and where it's yellow, that's the stretched location. Well, the amplitude is the center to center. That's the amplitude right there, as far as it is moved away from equilibrium. So the amplitude in this case is a length. In this case, it's an angle. But they're the same thing. They're the same thing. If you had a guitar string and you pluck the guitar string and you see the standing wave go up and down, it's physically how far the string is vibrating above or below where it normally is at rest. So if a guitar string is normally at rest like that, and you pluck on the string and you create what's called a standing wave, this is going to oscillate back and forth like that. Well, the amplitude is as far as it gets from its normal position. Well, that's just the amplitude right there. That's that height. Okay? What causes the amplitude to decrease over time? What causes the amplitude? I'll draw another graph so you can see it. to decrease over time. Damn. Hold on. What causes the amplitude to decrease? Travis, what do you got? Friction, yeah. And friction causes you to lose what? What's the key word there? It's a loss of energy. Amplitude measures energy. We wrote this down already earlier in the year that energy is proportional to the amplitude squared. So if you lose energy over time, you keep losing energy, you're losing amplitude. That's what allows the pendulum to eventually stop. The amplitude is decreasing and my arm stops eventually. Your legs are pretty much pendula. Think about it. When you walk, what do? Don't you swing your leg forward? It's like a pendulum. It's a pendulum with a joint. Your knee is the joint, right? So technically speaking, you have like a pendulum here, and your leg is also on a pendulum. It's like a pendulum within a pendulum. And these are actually really cool. There's a cool video. It's like an hour long. I didn't watch the whole thing. It's like the first 10 seconds all you have to watch. But somebody took a pendulum with a joint in the middle of it and spun it really fast, and it was very low friction. And the motion, because this kept swinging around, like the bottom half of the pendulum would swing over it, the motion was kind of crazy, and they modeled it with they followed it with a fluorescent light, and you could see the tracing of it, and it's really cool what it ends up looking like. But it's like a pendulum within a pendulum. That's what your leg is. Your leg is a pendulum that you're swinging forward, but your knee is a pendulum on your leg. So the lower half of the leg is its own pendulum. See that? But the upper half of the leg is a pendulum also. So it's like if your leg swings and your leg kicks back, it's two pendula together. It's like a coupled pendulum. We haven't done anything with that mathematically, but the concept should be like rather, not straightforward, but rather analogous to what we've been doing all chapter with pendulum. A skateboarder in a half pipe, it's a pendulum, right? Starts at the top. What does he do? To the bottom, back up to the top. To the bottom, back up to the top. So a pendulum is a way to model many things that follow this kind of a pattern. Okay? Skateboarder, snowboarder, whatever you want to think about for like a half pipe. All right. Let's talk about other terms. So we talked about amplitude. We talked about period. We talked about frequency. How about wavelength? Where does wavelength come into play? I mean, you just kind of did this with your lab, so this should be pretty straightforward in your mind. Marilyn?
The distance between the amplitudes.
The distance between the... Find a better word.
Crest.
Good, that works. So the distance between the crests themselves, the maxes, the peaks, whatever you want to use. I wouldn't say amplitudes though, okay? So this is the actual wavelength. Now, if you didn't want to measure from peak to peak, you could measure from the bottom to bottom or trough to trough. But can I do that on this diagram right here? Do I have two bottoms to this? No. So you really probably need to measure peak to peak. So again, wavelength can be crest to crest, trough to trough. Either way to think about it is fine, but there's only one trough in this picture. There's only one minimum value, and it's right here. So there's no other minimum to align this with further on, so I can't measure it that way. Another way I could measure it, though, is this. Instead of measuring it the way I currently am, I could simply put a dot in my origin and a dot here. And that's also one wavelength. That's also one wavelength. Those are the exact same values. Okay, why is it one wavelength? Remember, a wavelength is the length of the cycle when it's completed one full cycle. What's one cycle? Pendulum, starting here, there, and back. That's why you have to, ready? It's like you're going there and back, or there and back. You have to get back to your starting point by passing through equilibrium at some point in time. So the way I think about this is the pendulum at equilibrium. The pendulum has been raised up and then released. So right here is where the pendulum is. Here's my arm. I release my arm. It falls back to equilibrium. Then it goes all the way over to the negative side. Then it comes back to equilibrium. Then it comes all the way back over to where I started from. Did you follow on the board as I was doing that? Again, falling to equilibrium, beyond equilibrium to the other negative amplitude, back to equilibrium, and then back to where it started from. That's physically what's happening there. If you were to draw that with like a quick freeze frame, this one would be at max amplitude, then here it's at equilibrium. So I'm lining it up like this. And this next one is when it's at the amplitude on the other side, and then back to equilibrium. So the pendulum is swinging through equilibrium and then back to equilibrium as it goes through the cycle. Yeah, right.
What would the series be?
You need units, you need measurements. You can't determine unless you have a length. So this graph can be given in two ways. Either you can be given a graph where you have some sort of an amplitude, which units will vary, versus time. I should put S, I should put T. Or you can have it where it's versus lambda. So if I'm given a graph like this, and I measure from here to here, and the units are in meters, this is physically one wavelength. But if I'm given something where it's in time, the measurement from here to here, although it's technically like a wavelength, is our period.
So when it's the both ends of period?
No, they're both the same thing when you look at it, right? Look, from here to here is a period, from here to here is a wavelength. The difference is the units and what I'm measuring against. If I'm measuring amplitude as a function of time, this is called period from here to here. If I'm measuring amplitude as a function of how far it's actually vibrating back and forth, this is called wavelength from here to here. But wavelength and period are very, very similar. They both involve the distance from beginning to beginning, or crest to crest, or trough to trough.
Okay, like for this graph, I know the cycle includes the period and the cycle there, so I was just wondering.
Yeah, just because I didn't give anything like over here, I didn't give units or what this is a measurement of, this could be thought of as period or wavelength, really. The length from here to here, although we call that one wavelength, that could be the period length if this is measured in seconds, right? Because what is period measured in? Seconds. So based on what is measured in, you'll know which of the two it is. From your lab today, you recognize that period, in this case, wavelength and frequency are related how? Wavelength and frequency, what were they related? You just wrote it down, and like almost all of you got it right when I was checking through your labs. Wavelength, and frequency, how are they related to each other?
Isn't it like if the wavelength is double, frequency is half?
Yeah, so how is that related? Indirectly. Okay, and that comes about from this. This was our other equation that we utilized in section 13.3 and 13.4. This is very similar to another equation we had a little while ago, actually. Let me explain how it's similar in nature. So compare these formulas, please. Compare these formulas and look at them. They really are similar. If you solve for omega on the left here, you get V over lambda. Well, it looks like omega is inversely related to the wavelength. Well, it's also inversely related to the period, because what did Marilyn just ask a little while ago? She asked about period and wavelength and how they differ. Well, they're very similar, actually. They're both inversely related to frequency. Okay, so here you see the inverse relationship between frequency and wavelength, and inverse relationship between frequency and period. Okay, they're different values, though, because this involves V. What is V? Velocity. Okay, where V is velocity. So inversely related also. Hey, for these ones, you have to be given the V value. You have to be given the velocity. Or maybe I'll give you frequency and wavelength, and all you got to do is multiply them to get velocity. But it probably wouldn't be that. Okay, the velocity, if you remember, is either given or it's an EM wave, and they're all the same. Now you don't have to memorize that value. It'll be given on the test, but starting next section, you will have to have it. It's on your formula sheet, so you don't have to really memorize it. But in the next section, I'm not going to give you the number in the actual question. Let's talk about types of waves for a second. Let's stop and talk about types of waves. So we have two types of waves. We have transverse and longitudinal. So what's the difference right away? Transverse versus longitudinal? What do you mean? You're right. That's what everybody answers with. One's parallel, one's perpendicular. Parallel to what? What's parallel? What's happening? Close, but not really the right explanation.
The transverse one is perpendicular to the disturbance, right?
Okay, so for example,
Oh, if I had my arm and I had spread my hand like this.
okay, that's the good example. We use the example with like a vibrating blade, actually. But a rope in the hand is exactly that. So if you're causing a disturbance that causes the wave to look like this, and the rope is literally moving up and down, the rope keeps bouncing up and down like this, well, the wave is traveling left to right, and the rope is going up and down. So we can see that those two things on the board are perpendicular to one another. We did it with the slinky. My arm is a little messed up. I'll try to get it now. So you can even like, it's not working. We did it with the slinky to give an easy example, and this was literally it. All we did was talk about how when a pulse is sent back and forth, it's oscillating up and down. The actual spring is going up and down right now, yet the wave is going left to right. It's going back and forth. Okay, that was the example of a transverse wave. And I'll take one more. And a longitudinal wave, let's just keep it nice and flat. Okay. A longitudinal wave, the idea was instead of vibrating up and down, we vibrated forward and back. So it was sending a pulse like this. So the vibration is left to right, and the wave is left to right. So as I think Marilyn said, the disturbance is the word, right? It's the word you used, and that's the correct word. The disturbance for a transverse wave is up and down, yet the wave moves left to right. But for a longitudinal wave, you send a pulse to the right, well, it starts to vibrate like this, and then vibrate like this, and then vibrate back and forth, and then vibrate back and forth. So this is where the pulse is moving left to right, and yet the wave is also moving left to right. So this is parallel, and this is perpendicular. It's an ugly parallel symbol. Okay, these are parallel to one another. The vibration is left to right, and the wave moves left to right. This vibration is up and down, yet the wave moves left to right in that case. Waves, transverse. We talked about interference with waves. What was interference? What was that whole concept? Where did interference come in to play a role? What was interference? We had two types of interference. We had constructive and destructive interference. Constructive interference involved the slinky, where both ends sent a positive pulse. What happened to those two? They came together in the middle there. See how they're both jumping up in the middle? Because I'm sending a positive pulse this way and a positive pulse this way at the same time, the actual slinky is going to shoot up in the middle like that. Versus if I sent a negative pulse and a positive pulse at the same time, it's hard to do that one. They're going to do what to one another instead? What are they going to do instead?
Well, if they're both negative, they add on to each other. Anyway, they all add up to each other. So, like the two waves that are on top, they'll add to a really big positive.
Okay. And then what if one's on top and one's on bottom?
If it's the same, like negative 2 and 2, it'll be a straight line.
So in this case, good, you're correct, sorry. In this case, we have 5 and 2, let's say, as our heights. So these two waves are about to collide. When they do collide, they're going to coalesce. Is that a right word for that? What does that word mean? I feel like that means something like bring together, right? No. Coalesce? C-O-A-L-E-S-C-E? I'm trying to use bigger words these days because I've been reading more, but they're clearly not right. So this height, they combine to make a height of 7, okay, when they actually hit each other. And then the waves will continue and they'll pass through each other. So this little guy with 2 will continue on, and this bigger guy that had a height of 5 will continue on this way. So this is an example of constructive interference. This is seriously just the beginning of what you would use interference for, as far as physics is concerned. It's like just like the tip of the iceberg here. It's really simple for that reason. Either they combine in a constructive manner, or they combine in a destructive manner. This is a constructive manner, meaning they get larger as a result. If both waves had been negative, you'd have -5 plus -2, yielding -7. So if both waves are positive or both waves are negative, you have constructive interference. When do you have destructive interference? Yeah, when they're different. What do you mean by that?
Like one's positive and one's negative.
Exactly. So we've got a wave traveling this way and a wave on the bottom traveling this way. Well, when these two things come together, if this is a height of 5 and this is a height of 2, the answer is going to have a height of what? 3. Because the 2 is technically like a -2. The question is, which is bigger, right? If the top is bigger, the resulting wave is on the top. If the bottom is bigger, the resulting wave is on the bottom. Now, we took this concept and talked about graphs and using superposition. So let's quickly draw a little graph here. And let's draw a yellow curve that looks almost like a sine curve. And then another curve that's like increasing and decreasing like that. Let's say these two waves were interacting with each other, and the question said, let me give some numbers so you know. Hold on. Okay? Let's say the question said, after 10 seconds, sorry, I should put labels, time, amplitude. After 10 seconds, is this a case, or at 10 seconds, is this a case of constructive or destructive interference? Well, all you have to do is simply look at the two waves. At 10 seconds, these are the heights. Well, one's positive right up here, and one's negative down here. So clearly this is destructive. What would the resultant look like? Well, all you do is go over to the left. Well, it looks like that's around -1.9. Go over to the left. Looks like that's like 1.5. This is clearly not drawn to scale, and I can't draw straight lines. But you get the idea of what I'm saying where you move over? You'd have a grid line, obviously. It would not be drawn haphazardly like this. Now, if I wanted to see what that third line or where it would be, I could go ahead and mark off and say to myself, all right, what is this actual height? All right, that's about 1. What is this height? Around 2. So it looks like the result of this is a height of around, let's say -1.9. And on the top, this is a height of, let's say, 1. So I take 1.9 and add -1.9 to it, I get -0.9. So where would the resulting wave occur? It would be right here, on that dot in the middle. But that's only that one instant in time. How would I get the third wave overall? How would I get the third wave overall? How many times would I have to do this? How many times would I have to do this? Could be 3, could be 4, could be 5, it could be infinity. Because think about it. At every instant in time, remember I did this in class? I said grab a vertical line and draw a vertical line on the page somewhere. This vertical line, at any instant, the sum of these two waves has to equal the third. So if I add up those two heights right there, look where it crosses. Add up this height with this height, you'll get the result. So this is 0.5 plus 1.9, that's 2.4. So the resultant will be up here now. Then I go ahead and I move it a little bit. I take this and move it over to here now. Now I've got to add this height and this height together to get the result. Well, it looks like those are both constructive interference until I get in this range. Now, I'd be adding a positive height to a negative height, so my answer would be somewhere in between because it's destructive interference. So technically speaking, to get the resultant wave, you have to add up infinitely many of these. Add this up, add these up, add these up, add these up, add these up, etc., over and over again. You're not going to obviously do that on the test because it would take you forever. But I might give you an example with all 3 waves and say which of them is the result. Well, what you have to do is figure out which 2 add up to the third. So at this location right here, where I've got a vertical line, I could think about this. Is there any way I could add these two waves together and get this third wave up here? No, because look, this is negative plus another negative. If these were the original waves, let's say this followed some sort of a curve. Imagine this had a curve to it. So it follows some curve like that. And we say that these are the original waves, they would add up to give you this. And it doesn't make sense. Two negatives can't add up to a positive. But if I add these two waves together, I do get the third one right there in the middle. Okay, so we did this in your notes at the very end of this section, the very end. And I think we were like kind of running out of time at the end there. So you're supposed to watch that last bit of the very end of the video. Remember we kind of like ran through examine really quick that day? It was last Thursday. So the very end of the video, the last slide, if you're unsure of what I'm saying right now, needs to be studied at some point. Apparently.
Two waves in the negative is constructed, right? Correct,
because it becomes more amplitude, but on the negative side there. Okay, on the negative side only though. Questions you have had? Questions on problems set? Remember, I'm not here after school today. It's mornings from now on. That's why I emailed you guys yesterday as a reminder. Okay, office hours are only in the morning on Wednesday now. So I expect you to be there if you need help on this kind of stuff in the morning. I saw a couple today, which was good. I know it's tough the first day back from break, but it was this morning. Any questions you have on the problem set or anything you've been studying along the way? Nothing really? No? We got about 2 or 3 minutes left still. That's kind of my gist for the entire test. That's really all the material we've covered. We did something with the free and fixed boundary with the wave pulse getting sent back. We did something where there's like a pole here and there's a rope and the rope is connected to the pole by being tied around it. And when you send a pulse toward the rope, or toward the pole rather, when you send a pulse in that direction, it's going to cause this knot right here to slide up the pole. It's going to cause it to rise up. Well, the knot itself is going to want to pull back down, so as a result, it's going to send the same pulse back. As opposed to when we send a pulse to a fixed boundary, like a wall where it's connected, this is fixed right here. It cannot slide up or down. So because of Newton's laws, the pulse is going to be sent back on the bottom half. That was one quick theory thing we went over. There's not a lot of math to that. It's really just theoretical for that idea. I'm trying to think of what else you should be... Oh, you should be familiar with the prefixes. We talked about these last class. You need to know giga, mega, kilo. You know kilo already. You know centi already. You know milli already. The 3 that you know I've listed there. The other ones you haven't really gone over. I mean, we've gone over them. We went over them in the beginning of the year, actually. But we haven't used them recently. Giga. Giga is times 10 to the 9. Mega is 10 to the 6. Micro is 10 to the negative 6. Nano is 10 to the negative 9. Okay? So these symbols here, nano, micro, milli, centi, kilo, mega, giga, those are prefixes that you have to replace with these numbers. Feel free to look at the other classes' video. I did a couple extra different problems with them that I didn't do with you, and vice versa. Okay?